Hey everybody, welcome back to Organic Chemistry. My name is Todd Rothman, and in this video we're going to go over section 6, the final section for stereoisomers, and that is properties. So what properties do these isomers have? What makes them different? So number one, let's talk about one at a time, enantiomers. Enantiomers is, remember, where you have a mirror image or it's a complete opposite, like the left and right hand. So if you have one stereocenter and it's R, the enantiomer is S. If you have two chiral centers and it's RR, then the next one is SS. That's enantiomer, right? If it's RS, then it's SR for the next molecule. So these are just quick examples, and you're going to see that you're going to write this out often throughout the whole year because you're going to kind of jot it out real fast so you can remember the pattern. So remember, it's always the opposite. It's always a reflection, the mirror image of whatever molecule you're looking at. Now, it turns out that enantiomers, they have all of the same type of physical properties. Their boiling point's the same, their melting points are the same. Anything that you could think of as a physical property, like their dielectric constant, meaning how much they attract the opposite charge, it's the same. So they're really very similar. There's two things that make them different. One is written out here. It's called that it's the idea that they can rotate a plane of polarized light. We'll talk about exactly what that means in a minute, but another way to say it is that it has optical activity. I'll explain to you what this means in just a moment. But for now, let's just go through the concepts of what they can and can't do. Now, the fact that they have the same boiling point, melting point, that really presents a problem to us because most of our separation techniques that we do in a lab has to do with separating them based on a property. But enantiomers have all the same properties. The only other thing that they have that's not listed in my notes until now is that they have different biological activity. So they actually act differently. So for example, you might have a drug that will cure you in one enantiomer form, but the other one might kill you. So like it's really that extreme. So the way that enantiomers can act in our bodies is quite different. The R and S form, the enantiomer forms. Okay? So that's the only other difference between them. They can have different biological activity, but their properties are the same. Now, we'll find that this whole idea of biological activity is because of their handedness. So maybe one molecule can bind to a receptor, but another one can't in our body. It won't fit based on its handedness. So it's enantiomer, that'll be the thing. One can block something or maybe bind or not bind to something, and that obviously causes differences in our biological activity as to what we can do. Okay, here's another example, and then I'll move on. D sugar is a form of it's one type of a sugar form, an enantiomer form. It's called a D sugar. And we could use that for energy and such, but if we take the other enantiomer of sugar, like a carbohydrate, like an L form, then we couldn't do anything with it. It'll pass right through our system. It doesn't connect to our receptors. We can't break it down. We can't do anything with it. So that's another example, and they're just enantiomers. A D and L sugar, they're enantiomers of each other. It's just another language that we'll learn about later on next semester called D and L nomenclature. We'll learn about that then. But that's just another example. So let's talk about diastereomers. So a diastereomer is where you have an R and S within one molecule, for example, and then either an SS or an RR. So you notice how like this is never going to reflect because it's not complete opposite. So if they're not complete opposites, they're diastereomers. Another diastereomer would be like cis and trans, right? Cis and trans. They're also diastereomers, right? So these are diastereomers. If it's RS and then the next molecule either SS or RS, then, RR, then they're diastereomers of each other. Okay, so just remember this relationship here. So what does that mean? Well, if you have diastereomers, then they have completely different properties. They have nothing in common. Okay, so they have different everything, boiling points, melting points, dielectric constants. They have different reactivity in biological systems. Everything is different, all properties. So it's very easy to separate or to identify diastereomers you could boil them out at different degrees. You can separate them from different charge polarities. So there's a lot of ways to get them to move into different directions. Now, they do rotate polarized light, plane of polarized light, or they have optical activity as well, but there's nothing in common with them. So, for example, what we're going to learn about for enantiomers is that even though they don't have the same optical activity, they have a very similar characteristic to them. But diastereomers have nothing in common. They have no similar characteristics. They're completely different. Okay? All right. So we'll come back to this idea here. Now, this is an example. So let me actually explain to you while we're here. So let's say this is right here a pair of enantiomers, right? This is an enantiomer pair. And notice how if one has a plane of rotation of 19 degrees, so it rotates light 19 degrees plus, then we know for a fact that the enantiomer, the opposite of that, is going to be the opposite direction but the same magnitude. See, it's still 19 degrees, but it's just minus. So enantiomers, all they do differently is the direction of their rotation. They rotate light in a different direction, but the same exact magnitude, the same number. Diastereomers are completely different. So the fact that I told you that this is RR molecule is 19 plus, we can't use that to figure anything out about a diastereomer. So diastereomer, we don't know. It could be minus, it could be plus, it could be 19, it could be 100 degrees. Well, it could be 80 degrees or 50 degrees or 10 degrees, whatever. It's completely different. So there's no relationship between an enantiomer and a diastereomer. And diastereomers have no relationship with the enantiomers, right? So it goes vice versa, right? But enantiomers do have somewhat of a relationship, the same magnitude. All right, so that's what I'm showing you here. Now, I want to talk about a certain type of diastereomer, it's the mesoform. Remember, meso is where it's actually it's achiral. Remember, meso has a plane of symmetry within it. So just remember that meso is a form of a stereoisomer in which it's achiral. It's not chiral. And it turns out that if you're not chiral, you have no optical activity. It does not rotate light. So achiral molecules, meso or any other type, something that's not chiral, will never rotate light. It has to be chiral to do that. So it has no optical activity. It also has different properties because a mesoform compared to any of the other stereoisomer, it's a diastereomer relationship. So it's just like any other diastereomer, right? So if you have, let's say, a pair of enantiomers, you have, let's say, you have R for one molecule, and then you have SS for another, and you have RS, and you know that this is meso, right? Then you know that the meso molecule is a diastereomer to these two. That's the relationship. So because it's a diastereomer, it has completely different properties. But what turns out to be unique about meso is that it has no optical activity. And that's because it's not considered chiral. That form, meso, is really an achiral form of a stereoisomer. Okay? So it's kind of interesting if you think about that. So an RR is chiral, an SS is chiral, but an RS meso is achiral. Okay? All right. And then finally, the last way is what's called a racemic mixture. Racemic means, or racemate, same thing, racemate or racemic. They mean the same thing. What it means is that you have a 50-50 mixture of enantiomers. Now, it turns out that if you have a 50-50 mixture of enantiomers, it is completely different than any enantiomer by itself. So it's going to have different properties all around. It'll have different boiling point. It'll have different melting point. It'll have different optical. Actually, as a matter of fact, no, I should say it has no optical. No optical. So it actually cancels out. We'll talk about that in the next section. But the thing is that if I say to you that you have an enantiomer, an R whatever molecule, and then I say its boiling point is whatever, 25 degrees. And then I say, what's the boiling point of the racemic mixture of that molecule, where it's equal amounts of both enantiomers? It's not 25 degrees. It's completely different. Okay? It's a different number. So that's the thing. So a racemic mixture is a mixture of 50-50 of both enantiomers.